Okay, so like I said, we're moving into covalent stuff now. We're going to look at bonding in regard to how the molecules are arranged. We are going to make what we call Lewis structures, and then you guys are actually going to build the 3D molecules so you know what these covalent molecules would truly actually look like. So we got to start with a few kind of bits of information to make you guys understand everything else. Okay, so when we are talking about covalent compounds, they share valence electrons. So we're talking about covalent bonds. So we're talking about shared pairs of electrons, polar covalent or non-polar covalent. Okay, so we're going to start here with bond length. So this is the distance between two bonded atoms. Okay, so bond length is the distance between two bonded atoms. So if you look down here, move this. That's my organization. Okay. Let's see if we can. There we go. So, looking at our pictures down here, okay, this 147 picometers, the 134 picometers, and the 120 picometers, okay? Each of these right here, those are your bond lengths. Can you see, or do you need, if you can't see, you two can move to the front, if it's hard for you guys to see. Okay, so each of these distances, okay, measured in picometers, those are going to be your bond length. So you can put it right here wherever you want to put it. Bond length, little arrow, bond length. Really, I wanted you to put it in here, but that's just definitely not happening. So this is your bond length. Okay, so each one of these. So as we go from, this line represents a single bond, this line represents a double bond, and this line, these three lines represent triple bonds. So we'll go ahead and we'll label this. This is a single bond. And in a single bond, there are two electrons involved. So there is a single pair of electrons that are involved. That line represents two electrons. They spend some time around this carbon atom and this carbon atom. This bond right here represents a double bond. And how many electrons do you think are involved in a double bond? 4, I heard it. 4 electrons. And then if this is a single bond, this is a double bond, what do you think we're going to call this guy? This guy's a triple bond. Very good. And how many electrons are going to be involved? Good. You guys are on top of it on a Monday, so 6 electrons are involved. Okay, so looking at the bond length, as we go from a single bond to a double bond to a triple bond, what happens to the length of the bonds as more electrons are involved in bonding? I heard it. They get smaller. The distance gets smaller, right? 147 picometers, 134, 120. So as you move from a single, double, triple bond, or as you get more electrons involved in bonding, the bond length gets smaller. Okay? Let me find a place to write it. Let's just go down here. More electrons involved, shorter the bond. My handwriting's terrible. So more electrons involved, shorter the chemical bond. Now let's look at bond energy, and hopefully your handwriting's much better than mine and you've organized it better than me. Bond energy is the amount of energy needed to break a bond. There we go. So the amount of energy needed to break a chemical bond is your bond energy. So bond energy is measured in kilojoules per mole. So joules and kilojoules, that's just a way to measure energy. So in each one of these, you can do bond energy. And this is representing bond energy. And this is representing bond energy. So as you go from a single bond to a double bond to a triple bond, what happens to the bond energy? It increases. So the more electrons you have involved in chemical bonding, the more energy needed to break the bond, okay? Or released when the bond is broken, okay? So as you go from 2, 4 to 6 electrons, so let's say more electrons involved, more energy needed to break the bond. Okay, and we're going to come in, we're going to use these double, single, and triple bonds, making our Lewis structures. Okay, so move right here. Oh, it did not. So the picture did not actually come through, so we're going to draw it. So up here, draw a capital N, put a dot, put a double bond, put a single bond, put an oxygen here, put an oxygen here. I don't know why it didn't come through. 2, 3, 4. Okay, so this diagram is what we call a Lewis structure. Okay? So a Lewis structure is going to help us, it's just a diagram, that is going to help us figure out what the true 3D molecular structure is of the compound or of the molecule. Okay, this is one step to figuring out what it looks like in 3D. Okay, this is a two-dimensional diagram that tells us several things about the molecule. Okay, so first off, these right here, okay, these are called bonding regions. Okay, so this double bond, this single bond, they're considered bonding regions. Okay, you've got two atoms that are bonded together with some sort of covalent bond, a single or a double or a triple bond. So we call these bonding regions. Okay, these dots right here, what do the dots represent? You guys remember from just the Lewis structures? Louder? Valence electrons, okay? So these are valence electrons, but they're not bonded. So we call them lone pairs of electrons. They're electrons that are not involved in bonding. So when it comes to Lewis structures, there's two major type of regions. There are bonding regions and there are lone pair regions. The bonding regions, they're atoms held together with double, single, or triple bonds. The lone pair, okay, regions, they're just valence electrons that are not involved in bonding, okay? So in our Lewis structures, your atomic symbols are going to represent the nucleus of the atom and the core electrons. That's what your atomic symbols represent. It's the nucleus of the atom and the core electrons. Your dashes, okay, we got two dashes, one dash is here, These guys are shared pairs of electrons or bonds. If you want to think of the dash as shared pairs of electrons or covalent bonds. And then Brady just told us what the dots represent. These guys are valence electrons that are not involved in bonding. So valence electrons not involved in chemical bonding. And this diagram is going to help us figure out the true geometrical shape of the molecule. But we have to have a starting point. And this is where we start. Okay? So we're going to draw Lewis structures. We're going to draw these correct structures, but there's a few things you need to know. Okay? So the goal in drawing a Lewis structure, you've got two things. Okay? All atoms have to meet an octet or duet. So all atoms in your structure have to have 8 valence electrons, or 2. The first, we'll say the first 5 elements on the periodic table, but we were not going to use any metals. So basically hydrogen is the only one that's going to meet a duet. Everybody else is going to meet an octet. Okay? We have one more goal. So all atoms meet an octet or duet. Our second goal is that all valence electrons are accounted for. And I'll show you. This is one of those things that you just have to start doing it, and then you're like, oh, this is really easy. Okay? So we have 2 goals to get to our final correct Lewis structure. It's that all atoms have an octet or a duet, and all of our valence electrons are accounted for. We'll have to total them up, and we have to make sure that they are in our structure. Okay? Okay, so your central atom is this guy right here. Okay? So your central atom is basically in the center of the diagram. It is in the center of the diagram. It's the atom that's in the center of the diagram. Okay? Rule of thumb in regard to figuring out what atom goes. There's a few things. Okay? Trying to think, I might need a little bit more room. The first one, if carbon is in the formula, carbon is your central atom. Carbon is always central if in formula. If carbon is present, he always goes in the center, okay? And the reason he always goes in the center is because he has 4 bonding regions. Carbon has 4 valence electrons, so it can bond with 4 different atoms very easily. So he always goes in the center, okay? So I'm still on central atoms. I didn't give myself enough room. Okay, so that's one thing to go by if carbon is present. You can also go by the single atom that is present. So like up here, my formula would be BF3. So my single atom is boron, right? I have just a single atom of boron. So if carbon isn't present, that's one way you can look at it. You can look at the formula, and whatever the very single atom is, the lone atom, okay, is going to go in the center. Okay? We got one more rule of thumb. Or you're going to go by the atom with the lowest electronegativity. So atom that has the lowest electronegativity. So if you have, let's say you just have 3 atoms, okay? Let's say you have 3 different atoms and carbon isn't present, okay? You would have to look at each of their electronegativities. Whoever has the lowest electronegativity, he goes in the center. Okay? Your terminal atoms, these are the atoms, our three Fs over here, are three fluorine atoms. Those are our terminal atoms. So let's say outside atoms. Or you can say are bonded to the central atom. I'm going to put a big, huge, fat star right here. Hydrogen is always terminal. Hydrogen is never, ever, ever in the center because hydrogen can only meet a duet. Okay? So hydrogen is always terminal. It will never be a central atom. These are all rules to help us build or help us make one of these diagrams. So we're just gonna jump in and start drawing them, okay? So I went ahead and I gave you step-by-step information, okay? It takes so long to write all of that out, so that's why I just wanted to give it to you, okay? So these are the general steps. We are going to use this formula right here in a second to make a Lewis structure. So it says, count up the total number of valence electrons in all atoms involved. This is the number that should be in your structure. Place the central atom in the middle and place the terminal atoms around the center. Place single bonds between each atom. Place lone pairs of electrons on each atom until all atoms have an octet or duet. Okay? Hydrogen has a duet. Hydrogen will never get dots. He only gets a single line. We're going to count up all electrons in the structure. If your valence electrons equal the total number of electrons you calculated at the beginning, then you're done. If we have too many electrons in our structure, we're going to erase lone pairs, okay, off the terminal atoms. We'll make double or triple bonds until we reach our goal. And if we have too many valence electrons, we're going to add electrons to the central atom, and we'll talk about that in just a second. So let me get a different sheet of paper. And we are going to draw the Lewis structure for this guy right here. There we go. Okay. So our formula is HCN. Okay, so the first thing we have to do is we have to count up the total number of valence electrons. Okay, so I'm just going to do it off to the side. How many valence electrons does hydrogen have? 1. How many valence electrons does carbon have? 4. How many valence electrons does nitrogen have? Very good. So we're going to count up the total number of valence electrons for all of the atoms involved. So right now we have 10 valence electrons. So this is our goal. Our goal is to make sure every single atom has met an octet or a duet, and we can account for 10 valence electrons. Okay? So first thing you do, you figure out what the central atom is, and in this case, what is the central atom? It is carbon. Hydrogen is always the terminal atom. Okay? If carbon is present, go smack dab in the center. And then I'm going to attach all my other atoms with single bonds, and I'm using a pencil because I'm probably going to have to do some erasing. So I attach whatever other atoms with single bonds. And then what I'm going to do is I'm going to add dots until each atom has reached an octet or a duet. Now don't forget, each line is a shared pair of electrons. So each line represents 2 electrons, which is shared between each atom. So this line is 2 electrons, okay? Those 2 electrons go to the hydrogen and go to the carbon. So right now, hydrogen has 2 electrons. So he's met a duet, he's happy. We never put dots on hydrogen, okay? Right now, carbon has 2 4. but we need to have a total of 8. So I'm going to put a shared pair of a lone pair of electrons here and a lone pair of electrons here. So now carbon has 2, 4, 6, and 8, and he is happy. Nitrogen right now only has 2. So I'm going to add my lone pairs until he has 8. So 2, 4, and our valence electrons, those dots always come in pairs. Just like the lines are a pair, your dots come in pairs as well. So that's the first thing that we're going to do. Now I have to count up. The goal is to have each of these have an octet or a duet, and I can account for 10 valence electrons. So if I count them up total, I've got 2, 4, 6, 8, 10, 12. Right now I have 14 electrons. That is way too many. Okay? So I can't just have more electrons than all of my atoms have. So the next step is I'm going to get rid of lone pairs and make them lines or dashes. Okay? So every time that I put a new bond in here or a new dash, I have to take a pair of electrons off of each atom. So I'm going to erase those. That's a terrible eraser. And I'm going to add a double bond. Okay? I have to erase a pair from each atom because that line represents 2 electrons that are shared by each atom. So now I have to check both things. Do I have an octet or a duet? And do I have 10 electrons? Mac, please, I don't want to have to reteach this. I'm getting old and I'm tired. So 2, 4, 6, 8, 10, and 12. So right now, if I leave a structure like this, I've got 12 electrons, and really I have to have 10. So then I have to go one step further. Get rid of my double bond, and let's make it a triple bond. Okay? So I'm going to get rid of a pair of electrons here, and a pair of electrons here. And I'm going to add a triple bond. I can't ever add a double or a triple bond here because hydrogen can only have 2 electrons. So now, make these a little bit darker, easier to see. Okay, so now I got to count them up. Hydrogen has got 2, he's happy. Carbon has 2, 4, 6, 8, he's happy. Nitrogen has 2, 4, 6, 8, he's happy. Now we have to see if we got 10. So we've got 2, 4, 6, 8, and 10 electrons. So this is my correct Lewis structure. Okay, I'm going to rewrite it since my eraser was really kind of crappy. And this is the correct Lewis structure. So it's just a matter of actually doing a bunch of them. Okay, so let's do, before we talk about expanded octets, let's do another one. So if you flip your little packet over, and let's do letter A, which is CH2O. Let's do the Lewis structure for CH2O. That might be. Okay, so the first thing we are going to do is we are going to add up the total number of valence electrons in this structure. So I'm going to start with, I'm going to just list all of my atoms. Carbon has 4 valence electrons. See how I have 2 hydrogen atoms? I have to count for both. So I have 2 hydrogen atoms, each with 1 valence electron. So together there's 2 valence electrons. Oxygen has 6 valence electrons. So I'm going to add them all up. I've got 4, 6 is 10. So this time I have to count for 12 valence electrons. Who's my central atom? Carbon. So I'm going to stick him in the center, and I'm going to attach everybody else with single bonds. Okay? And it doesn't matter how you want to attach them, like where they go. I'm going to put hydrogen here, and oxygen here. Now I'm going to add dots to make sure everybody's got an octet or duet. Hydrogen never gets dots because he's happy with the straight line. but I need to make sure oxygen and carbon have the correct number. So I'm going to add 3 pairs of electrons on oxygen, 2, 4, 6, 8. Right now carbon has 2, 4, 6, so I need 1 pair right here. Now I have to see if I've hit 12. 2, 4, 6, 8, 10, 12, and 14. That's too many. I need 12, right? So I have to get rid of 1 pair of electrons on my central atom. And I'm going to have to get 1 pair of electrons off of my oxygen. I should have used that crappy pencil again. And I got to make, this is the only place I can make the double bond. I can never make a double bond here. So right now carbon has 2, 4, 6, 8, so he's happy. Oxygen has 2, 4, 6, 8, and he's happy. So now let's see if we have a total of 12. 2, 4, 6, 8, 10, and 12. So that is my correct structure, and I'm only going to rewrite it because I did not use whiteout. So this is my correct structure. Let's just do one more. Let's do H2O. First thing we're going to do is what? Count them up. So I have hydrogen. I have 2 hydrogen atoms with 1 valence electron each, so that's 2 valence electrons. I have 1 oxygen atom with 6 to give me a total of 8 valence electrons. Who do you think is going to be our central atom? Because we do not have any carbon. Oxygen. He's my loner. He's by himself, so I'm going to stick him in the center. I'm going to attach each atom to the side. Hydrogen, do they get dots? Yes or no? No. But I need to make sure oxygen has got enough. So I've got 2, 4, 6, 8, and he's happy. Each hydrogen is happy, and I've met this. So that is my correct Lewis structure. Okay? Now let's go back to where it says exceptions to octets. Okay, so there's always exceptions to the rule in chemistry, no matter what you do. So some of these atoms, when they are found in a covalent molecule, can actually have more than 8 electrons surrounding it. Okay, so sometimes they take some electrons from like the 3D level or from the from some of the core electrons, and they get involved in bonding. Okay, and these are the ones that do that. Okay, so some atoms involve the electrons in their d sublevel when bonding. We say they have expanded octets. Okay, they can take more than 8 valence electrons when bonding. So phosphorus can take 10. Okay, so that means he could have 2, 4, 6. So instead of having an octet in the center, he could have an extra pair of electrons, just when he's in the center. Okay? Sulfur, 12. So that means when sulfur's in the middle, he could have 2, 4, 6, 8, 10, and 12. So he could have more than those 8 surrounding him when he's in the center. Xenon is 10. Chlorine is 10, and let me make sure I didn't screw up because my memory is that bad. I think it's, make sure my numbers are right. 10, 12, oh, I got these 2. Sorry, I got these 2. This one's 10 and this one's 12. There we go. And chlorine is 10 as well. There we go. So, boron is the opposite. So in that structure, in the very first, that looked like this. on the very first page. Boron is actually, he's in the center. Boron will be happy with 6. He's stable with 6. So that's why there's no lone pair of electrons right here. He's got 2, 4, 6. So he's happy with less than 8 electrons, and he's stable that way. Okay? Now let's do an example so you can see. Because normally what you'll do is you'll draw the Lewis structure and you'll be like, oh, this guy has an expanded octet because I have an extra pair of electrons that I don't know where they go. That's usually how you figure it out. And you're like, oh, now I remember. So let's look at xenon tetrafluoride. Okay? Let's do the Lewis structure for this guy. Okay? So we just start out like we normally would. Okay? We're going to count up the number of valence electrons for each atom involved. Xenon has 8 valence electrons. We have 4 fluorine atoms, right? Each have 7 valence electrons to give me 28 electrons total. I'm going to add those up, and does that give me 36 if I'm correct, right? 36 electrons we have to count for. So which atom is going to be our central atom? Very good, xenon. So we're going to start with xenon in the center, and we're going to attach all of our fluorine atoms. And then we're going to make sure everybody's got an octet. And then we're going to count them up. So I'm going to add my valence electrons right here. Or I should say my non-bonding electrons. And now I'm going to count them up. And let's see what I've got. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, right? Right now I have 32 electrons. But how many should I have in there? Should have 36. So this is where you're like, well, I've got 2 extra pair of electrons. Like, where are they going to go? Okay. This is usually when you'll be like, oh my gosh, this guy has an expanded octet. Right? Because we can't make single bonds into double bonds because fluorine would not have an expanded octet, okay, because he's on the outside. So the place that we would put our extra electrons are on the central atom, and this is how it looks. And it doesn't matter which side. Usually put one pair kind of off to the side and another pair off to the side right here. So xenon, 2, 4, 6, 8, 10, and 12, like I said, he's got the expanded octet for 12. So you'll usually, and you don't run into this that often, but you'll usually figure it out when you've put all the electrons where they're supposed to be, and then all of a sudden you're like, ooh, I got to stick a few more pairs in here. And that's usually when you're going to figure it out. Okay. Let's move on to polyatomic ions. You just have to tough it out. It sucks, but that is the way it is. Okay. So Lewis structures for polyatomic ions, they're super similar to just neutral molecules. So far, everything we've done is just a neutral molecule. Okay? But of course, our polyatomic ions have a charge, and that charge comes from either fewer electrons or extra electrons. If you have a negative charge, there's extra electrons in the mix somewhere. If you have a positive charge, that means in that mix of atoms, we're missing an electron or several electrons, depending on the charge. Okay? So when finding the total number of valence electrons for polyatomic ions, we're going to add 1 electron for each negative charge present. Or we will subtract 1 electron for each positive charge. This is the charge I'm talking about. Okay? Or this is the charge I'm talking about right here. So if I was doing the polyatomic ion, the Lewis structure for bromate, since I have a -1 charge, I'm going to add 1 electron to my total number of valence electrons. Okay? For perchlorate right here, I have a -1 charge. That means I'm going to add 1 electron to my total amount. Ammonium has got a positive charge, only 1, so that means I'm going to subtract 1 electron from my total. So let's look at chlorate. Sorry, perchlorate. ClO4 1-. Okay, so the Lewis structure, 2 things that are different. You have to count for the negative charge, and we're also going to put brackets around our polyatomic ion. So I'm going to start by counting up my total number of electrons. Chlorine has 7. I have 4 oxygen, each at 6 valence electrons, to give me 24. And that will give me 31 electrons. Except for I have a negative charge. However many negative charges I have, I'm going to add that to my total. So I'm going to add 1 more electron to make it 32 valence electrons that I have to account for. So who's going to be my central atom? Chlorine. I'm going to attach every oxygen atom. I'm going to make sure everybody has got an octet. Now I have to see if I hit that 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. Everybody has an octet. I hit my 32. So this part of the structure is correct. But since it's a polyatomic ion, I'm going to put brackets around it. And I'm going to put a charge on the outside. So those are the 2 things that are different with polyatomic ions versus just neutral molecules. You're going to have to either add or subtract the number of valence electrons according to the charge, and you're going to have to put brackets with the charge on the outside of it. Okay? We'll stop there. We'll do formal charges and resonance structures tomorrow. I've been writing quite a bit. Okay, no assignments. You can rest your hands.